So today we want to look at some rational functions, and the parent function of our rational function is y equals 1 over x. So if it was written in function notation, f of x equals 1 over x. So a way to quickly do this is we can think about starting with some inputs, like from -3 to 3, counting by ones, and seeing what we get out. So if we put in a -3, that would be 1 over -3, that would be 1/3. So we'd have -3 1/3. I could put in a -2, which would give me a -1/2. I could put in a -1, and that would be 1. If I put in a 0, that would be 1 over 0. And we know from previously talking that anytime that you have something and you're trying to put it into nothing, that's not possible. So we say it's undefined. So I'm not going to be able to use that input of 0. If I use an input of 1, I'll have 1 over 1, which is 1. An input of 2, that would be 1 over 2, so 1/2. An input of 3, that would be 1/3, and so on. So we could keep doing this to get some points, and then we could generate our graph. And so by doing what we talked about, our graph is starting to look like this. And as you notice, a couple things are happening. Our graph is not touching the y-axis, nor is it touching the x-axis. Well, why is that happening? Well, if we're talking about the y-axis, that means we have an input of 0. We said if we put 0 into the function, we have 1 over 0, and that's undefined. It's not possible. That's why we're not able to use that input of 0. It's not going to touch the y-axis. So if it's not going to touch the y-axis, what else do we know about this function? Well, we know we're not going to have any y-intercepts. Now, we also see that our graph is not touching the x-axis. Well, why is that happening? Notice how x is in the denominator. So any number that I pick for an input, notice how it's going to be going in the denominator of that function, which means it's going to be getting smaller and smaller and smaller as that value gets larger. If I'm putting a small value in, then it's having a larger output. But notice, every time that I put a value in for x, I'm going to end up with something. I'm not going to end up with nothing. Therefore, it cannot have an output of 0, which would be touching the x-axis. So because we're not able to use those things, we have some asymptotes. We've got an asymptote at x equals 0. We also have an asymptote at y equals 0. So again, this is what's happening with our parent function, 1 over x. We can see that we cannot have an input of 0 here. That's our vertical asymptote. We cannot have an output of 0. That's our horizontal asymptote, which means we can't have any x-intercepts either. So if we're talking about key features, no x-intercepts, no y-intercepts. We do have the two asymptotes, one vertical and one horizontal. So how are those asymptotes going to affect your domain and range? Well, your domain, the set of all the inputs, the x values, we can use everything but x. Same thing for the range. We can use all the outputs except for that output of 0 for the y. So how does that impact our values? Well, we're going to have to show that we're using all of the inputs for x except for 0. So see how everything less than 0 is being used, as well as everything greater than 0 is being used. Because we have these two pieces to our domain, we're putting them in union with each other. So it looks like a capital U. That's our union symbol showing we've got two pieces to our domain. Same thing with our range. We can use all the values less than 0 and all the values greater than 0, just not 0 itself. So that's our parent function. And with all of our other functions, we've talked about, well, how can we take these and transform them? And remember, we talked about doing lots of transformations. We can reflect, we can stretch, we can shrink, we can shift things left, right, up, and down. How does that show up in the equations for these functions? And so what we're going to focus on today is looking at a couple of these types of functions, still rational functions, but look at changes to the a value and the b value. So if you open up your Desmos activity calculator, I would select one at a time. So if you look at your a value, see how it changes, and then do the b value and see how it changes. After you do them individually, I would then try moving them in tandem to see if you can make predictions and seeing what happens. So we have a snippet of our Desmos activity here. If we start moving A, again, this is where an A is 1. Here's your sample table of values. What happens when A is greater than 1? Well, we can see that it's increasing faster than it was before. Some people say, see how it's pulling away from your axes. Now, what happens if it gets smaller, right? If we went less than 1, what would happen? We'd see that it would be getting closer to your axes. What would happen if A was negative? Well, that would be the opposite of these values, so we could have things in reverse. Let's take a look at B. So here B is at 0. Let's see what happens when B is greater than 1. See how it's moving to the right. Okay, let's go back here to 0. What happens when it's less than 1? See how it's going to the left. Now we have to be careful with these shifting right and left because our function standard format is x minus. So when it was a positive, it still stays x minus that positive value, but if it's negative, well, subtracting a negative, that's a positive, so it's going to change how we're writing our function there. So some things that we noticed, again, changing the a value for the graph, couple things. When a is greater than 1, it increases factor, that would be a stretch. If it was between 0 and 1, it would be slower, a vertical shrink. And if it was negative, we'd know that would reflect it over the x-axis. Again, with the b values, when b was less than 0, the negative number, it's really going to the left. Again, that expression would change to a plus b. And when it was a positive number greater than 0, notice how it shows up in the function as a minus b, it's shifting it to the right. So if we can identify those items within our template for our function, we can predict the changes and use the parent function table to make those transformations happen. So let's take a look at an example. Here we have our function y equals 3 over x. So what I'm going to do to start is I'm going to fill in my parent function table. So remember, we went from -3 to 3 counting by ones, and we just substitute them into that pattern 1 over x, and we had the outputs. So here is our parent function table for y equals 1 over x. Now I want to look at my equation here to see what kind of transformations are occurring. So if this is my parent function, I look at this one, notice how there's a 3 in the numerator when it was originally a 1. So what kind of change is that? So the numerator part, that's an output change, and it's a multiplier. It means these outputs are being multiplied by 3. It's 3 times faster than it was before, a vertical stretch of 3. So I'm going to take all of those outputs and multiply them by 3 and see what happens. So as I multiply all the outputs by 3, look what we get. We've got a -1, a -3/2, a -3, 3 over 0. Well, that's still undefined. We can't take 3 things and put them into nothing. They're still going to exist, so that's still undefined. We now have a 3, we have a 3/2, and we have a 1. So how are we going to make our graph? Well, these are now our new outputs, and our inputs are still here. So we're going to plot the point -3, -1, -2, -1/2, and so on. Notice how a point should not be plotted at 0 because we do have an output that's undefined. So if I'm plotting those points, connecting them to show it's a continuous function, what would it look like? It would look like this. So what do we know? If we have an input of 0 that's not defined, that means we won't have a y-intercept. It also means we'll have a vertical asymptote. Do we have any x-intercepts or outputs of 0? We do not, so it means we have a horizontal asymptote. And we won't have any x-intercepts. So for our asymptotes, our vertical asymptote would be at x equals 0, and our horizontal is y equals 0. How does that impact our domain and range? Well, it means we can't use 0 for either of those. So our domain would show that everything less than 0 and greater than 0 can be used, but not 0 itself. Same thing for the range. Anything less than 0 for an output is okay, or greater than 0 for an output, but not 0. So again, we've got the two pieces and we're putting them in union with each other, showing that 0 is excluded from the range, the outputs, as well as the inputs from your domain. Now, if we take a look at this function, y equals negative 2 over x, let's see how we can apply the same principles. So what kind of transformations are being performed? And again, we're comparing this to the function 1 over x. Well, we see two changes. We see this negative, so we know it's got to be a reflection of the original, and we see this multiplier by 2 times faster. So we've got a reflection over the x-axis, and we've got it 2 times faster, which means it's a vertical stretch. So we're going to apply those to our parent function table. And again, this is just showing you our parent function, the inputs and outputs of 1 over x. So again, the reflection over the x-axis, that's going to be an output change. So we're going to have to take the opposite of all these outputs. A vertical stretch of 2, again, that's another output change, so we're going to have to take that result and then multiply them by 2. So here's the part showing the reflection over the x-axis, again, taking the opposite of all of those values. And then we're going to apply the vertical stretch of 2, multiplying by 2 for all of those output values. So that last column on the right, those are going to be the outputs for our points, and our inputs are here in the x column. So we're going to plot the point, negative 3, 2/3, negative 2, 1, negative 1, 2. 0 is not going to have a point because it's undefined. 1, negative 2, 2, negative 1, 3, negative 2/3. So by plotting those points, generating our graph, it looks something like this. So as we look at the graph, we can see we're not going to have a y-intercept because we could not use that input of 0. So we're going to have that vertical asymptote here. And we're not going to have any x-intercepts because we've got that horizontal asymptote coming into play. So how does this impact our domain and range? Well, because we have those two asymptotes, we know 0 cannot be used for either of them. So we're going to have to show that 0 is excluded from the domain and range. How do we do that? Well, we're going to put our pieces in union with each other. So here we show that all the inputs less than 0 and greater than 0 will fit for our domain. All the outputs less than 0 but greater than 0 will work for our range. So let's try this function, y equals 1 over x plus 4. And again, we're comparing it to the parent function, y equals 1 over x. So our eyes should be drawn here. And we have to know, since it's an input change, inputs go horizontally. So this is going to be a horizontal shift. The question is it going to go to the left or to the right? So again, I'm just pulling up my parent function table that we've been working with from the beginning, 1 over x. And again, as we think, input changes are the inverse as they appear. So even though I see plus 4, your instinct might be saying, oh, I'm adding 4 going to the right. No, it's the inverse of how it appears. You're really going to the left. Because remember, the standard form was x minus the value. So the only way we can get a plus here is if you're subtracting a negative. So we're going to be going to the left 4 units of where we were before. So I'm going to take all these inputs and move them to the left. So mathematically, what operation is that? Well, that's a negative value, right? So we're going to the left 4 units. So if I take all these inputs and move them to the left 4, where do we end up? That would be here. So if we're graphing, we're going to use these as the inputs in blue, and we're keeping the original outputs to make our points. So when we make our graph, what is that going to appear like? It would look like this. And remember, your input here now at negative 4, because the output is undefined, we cannot use that for our graph. So that's our clue that we're going to have a vertical asymptote here at negative 4. Again, we shifted everything to the left. So originally that was at 0, so the asymptote moves with it. Well, will we have any x-intercepts? No, we're not going to have any x-intercepts because we didn't move that Yes, the horizontal asymptote, right? The output of 0. But notice, by shifting everything to the left 4 units, we do have a y-intercept, and we can see that on the graph, meaning there's an input of 0. Now, you could add one more step to your table and see where that is. You could put 0 into your function to see what you get out, and that would tell you the coordinates for your y-intercept. So our y-intercept would be at 0, 1/4, or 0.25. It's a quarter. Again, to recap your asymptotes, you have a vertical asymptote now at x equals -4, and the horizontal was unchanged at y equals 0. So because of this shifting, that impacted your domain. So again, we're using all the values less than -4 and greater than -4, not -4. The range was unchanged. We're using everything less than 0 and greater than 0, not 0. Let's try one more function. Here we've got y equals 1 over x minus 2. So again, thinking about how we're comparing it to the parent function, 1 over x, we know that down here in the denominator is our change. So if we see x minus 2, what kind of transformation would that be? Well, because it's with the x, it's got to be horizontal, and it's the inverse of what it appears. Again, you might want to say, oh, we're taking away 2, we're going to left. No, it's the inverse. That means we're going to the right 2 units. So I'm going to use my parent function table, right? And we're going to shift this all to the right 2 units. So what is that going to look like? All these inputs are going to go to the right 2 units. So what operation are you doing? Technically, you are adding 2 to every single input for your function. So if we add 2 to every single input, what will we end up with? We'll have these values here. So here's the inputs that we're going to end up graphing and their corresponding outputs. And again, notice the input of 2 has an output that is undefined. So nothing is going to appear with that input of 2 on your graph. So if we plot those points, here's our basic rational function. Now again, to show you cannot use that input of 2 for x, we can draw our vertical asymptote. And notice how your outputs, again, they're not going to have an output of 0, so we can draw in our horizontal asymptote. So since we can't have an output of 0, that means we're not going to have any x-intercepts. But by shifting it to the right 2 units, notice how we do have a y-intercept. And this is nice because it shows up on our table. An input of 0, there's your output. Your y-intercept is at -1/2. And again, your vertical and horizontal asymptotes. And because we shifted it to the right 2 units, that's going to impact your domain. So we can use everything less than 2 for an input or greater than 2, just not 2. Range was not affected. So again, we can use everything less than 0 or greater than 0, just not 0. So at this point, you're going to do some more practice with the transformations, graphing your rational functions, again, relating it back to the parent function, 1 over x, identifying just like we did in our table to get at least, I would say, 5, 6 good points to plot to form your graph, and then talk about the key features, any x or y intercepts, asymptotes, and domain and range.